Okay, in the last class we saw how to find the logs of various numbers. Now, a few things to note. The log of a negative number is not defined, it does not exist. So if you use your calculator and try to find log of -5, you will get an error message. So remember, logs are always of positive numbers. So log of 5 makes sense. Log of -5 makes no sense. Okay, now moving on to a very important exercise, and that is converting log statements into equivalent exponential statements. Now first let's look at the definition again. So I'll write down here the definition of the log statement again. So that is y is log of x to base a, which means that a raised to the power y is x. So remember, this is the log version and this is the exponential version. So what we're going to practice now is converting log statements into equivalent exponential statement. So one very mechanical way of doing it is as follows. So let's start with this example. So suppose I have log of 25 to base 5, which is equal to 2. Now I want to write it as an exponential statement. So first let's find each of the three things. The y is clearly 2, a is 5, and x is 25 from here, comparing it to the definition from here. So now that would be a raised to the power y equal x. So a is 5 raised to the power y. Y is 2, and that must be equal to x, and x is 25. So this exponential statement is equivalent to this log statement. Okay, let's do one more. So suppose I want to do this one. So y is log of m and base is 5. So clearly this is the a value, this guy is x, and this is obviously y. So therefore the equivalent statement would be a, which is 5, raised to the power y, which is y in this case, equals x, and x happens to be m. So this is the answer. Next one. So now we want to do it for this guy. So 7 is equal to log of 10 to base a. So what's the equivalent of it? So its exponential equivalent would be a raised to the power y. So a is a, y is 7, equals x, and x is 10. So these two are equivalent statements. And finally, this one, ln of b is equal to 3. Now remember, whenever you see ln, it actually means log, and the base is e, of b equals 3. So this guy's equivalent would be a raised to the power y. So a is e, y is 3, and that should be equal to x, and x is b. So this is the equivalent statement. So you have to practice writing log statements into equivalent exponential statements in your homework, in MyMathLab, as well as other practice sheets. Now we are going to practice a reverse problem, That means we're going to be given the exponential statement and we have to write the log statement. Let me write the definition again. So the definition was y equals log of x to base a, which was equivalent to a raised to the power y equals x. So this time we are going to go from this way to this way. Okay, so let's start with the first one. 2 raised to the power 5 is 32. So what is its equivalent? Now compare it to this. So you would notice that a is 2, y is 5, and x is 32. So therefore the log statement would be log of x, which is 32, the base is a, which is 2, equals y, and y is 5. So this is the equivalent log statement. So let's try the next one. 8 raised to the power 1/3 is 2. So the equivalent would be log of x, and x is 2, base is 8, and that will give you the y, which is 1/3. So these two are equivalent statements. Similarly for this one, it would be log of 7.5, the base would be 5, and this would be equal to y, and that is n. So this is the equivalent log statement. And finally, for the last one, you would have log of c, base is e, and that will give you n. Now this one would be written as ln of c equals n. The reason is because log to the base e is same as ln. Again, you need to practice quite a few of these. Now let's move on to the properties of logs. So the first set of properties are directly derived from the definition. They are not very important. I mean, one should understand them, but I can pick on few of them to explain the logic behind it. But these are not so very important. So let's look at the first one. So this guy says log of 1 to any base a is 0. Now that is obvious, because remember what is log of anything means. It means a raised to what power will give me 1. What should be the exponent of a so that I get 1? Well, obviously it must be 0, because a raised to the power 0 is 1. So therefore log of 1 base a is 0. Similarly, let's look at another one. What would log of a to base a be equal to? That means a raised to what exponent gives me a? Well, this exponent must be 1. So it's 1. In other words, so suppose if you see log of 5 to base 5, what is it? It's 1, because 5 raised to the power 1 is 5. Okay, here are the more important ones. Now this would be needed in our next set of questions. So here are the three properties. The product property, which says log of x times y is actually log of x plus log of y. The quotient property is log of x divided by y is log of x minus log of y. And finally, the most important one, the power property, it says log of x to the power r is same as saying r times log of x. Now the base is same, so you don't have to keep saying the base because it's the same base. So let me explain each one again. So suppose one has log of, let's say, 5 times x and the base is a. Then according to this property, this would mean log of 5 plus log of x. 5 times x splits up into log of 5 plus log of x. Similarly, suppose you have log of 7 over 5. Then this could be written as log of 7 minus log of 5. Now these things are not intuitive, so you would have to remember them and get used to thinking in this particular way. The power property, as I said, is very, very important, and it says the following: log of, now notice I'm not writing any base, so if I don't write any base, that means base is 10. But it really doesn't matter. All these things work as long as you have the same base in the equation. So suppose you have log of x to the power 5. So you have log of x to the power 5, so that would be 5 times log of x. So this exponent comes and sits in the front in this manner. Now again repeating, these properties are not intuitive, and if you think algebraically, you would make mistakes. A classical and a very common error is the following: log of x plus log of y. The temptation is to say that would be log of x plus y, and that is not true. So again repeating, if you see log of, for example, x plus y, a lot of times people say this is log of x plus log of y, as if log is some kind of multiplier which you can distribute. That's not correct. So please don't make this mistake. So one would think, what is log of x plus y? Well, there's nothing you can do about it. Log of x plus y is log of x plus y. You cannot break it in this manner. Some more warnings. So these are also pretty common mistakes that people make. So log of 5 over 2. So if you have log of 5 over 2, do not make this as log of 5 divided by 2. That's not true. Similarly, log of 5 minus log of 2. It's very tempting to say that this would be log of 5 minus 2, which is log of 3. No. Similarly, log of 6 over log of 2. Sometimes students think that 6 and 2, I could cancel them and make it 3, so log of 3. That's not true. Log of 6 divided by 2, the whole thing, This is very, very wrong. This is not at all log of 3, so don't do this either. So in other words, do not think algebraically like in your algebra. Do not think algebraically. Just follow these rules strictly. Okay, we'll continue with examples of using this in the next session.